So we screwed up, to put it mildly. I've gotten a lot of very constructive feedback. Believe me when I tell you that my point in assigning the homeworks to you was not to cause you to have lack of sleep or to increase your frustration level, because I'm not particularly sadistic myself. So the problems with homework 8 were not intended, and I do sincerely apologize for the frustration that they caused. I think this is not excusing it. This is just sort of explaining why it happened. I think part of the problem is we rushed it out because people were mad at us the week before, understandably, for getting it out late. So we ended up trying to get it out a bit faster than we should have, and it wasn't fully developed, hence all the problems that you ran into. So I do apologize for it. It was certainly not my intent. I want to make you enjoy computer science. Homework 9 was not the way to go about doing it. That being said, there's a number of things that I'm planning on doing that will both somewhat compensate for it, as much as it can be, being as you probably already lost a couple nights' sleep, and also prevent this in the future. So homework 9, I'm going to talk a bit about homework 9 today. Not surprisingly, we're not going to release it today because, well, I think homework 9 is going to solve a lot of the issues that happened with homework 8. We want to spend a bit more time to look over it a bit more closely. The grading for homework 8 will be on the very easy side, just because it doesn't seem fair for me to give you all 60s after you spend all that time on it. So those are my thoughts on homework 8. I'm interested to hear your thoughts. There you go. Well, keeping in mind that this is recorded, yes.
I mean, the only thing I thought was that the cell item method was a bit strange, and that was the only thing.
Yes. So there was a comment on the cell item method. Any other hate mail or No, I didn't. Oh, I wasn't saying you did. Don't worry. Other comments, wrath that needs to be vented? Yes.
I think the worst part of the homework with the depot class, that was the one I had the most trouble with. Because the method, the one we had, it was also messed up. I mean, it was just hard with the figure out because I kept cutting so many errors because one type is static and the other is convoluted. And it was also trouble because of the vehicle. I mean, I really didn't understand that I needed to create my own vehicle object in order to get that method going.
So what he was saying is, if I could paraphrase it, the depot class required a lot of dependencies, required the vehicle class and a couple other things, and we hadn't fully given you the dependencies, which was part of the concern. For this upcoming homework, we're going to be looking at the party class and the vehicle class. We were originally going to give you the control class, but again, we thought that had a lot of dependencies, so it probably wasn't the best way to go about assigning the homework. The classes that we're giving you for homework 9 are going to be somewhat less on the dependencies, so I'm hoping that will solve it as well. Any other comments? Constructive, not so constructive? I do encourage, if you do have other things you'd like to say or wrath you'd like to vent, please feel free to send anonymous feedback. Obviously, if it's constructive anonymous feedback, it helps me improve for the future. So that's probably all I'll say about homework 8. Again, I am sorry for the frustration it caused. So homework 9, I'm going to spend some time talking about it. Question? Oh, yeah. Oh, yeah. I'm definitely planning on going easy on the grading because, again, it's not fair for me to give you all 60s or 40s when it was really our fault that the homework was that bad. Okay. So homework 9, I'm going to spend some time talking about it. We have a whopping 2 full weeks of classes after this week. Next week, the following week, and then there's like Monday and Tuesday of the week after that, which means after today, there's a total of 7 more lectures for me to cram as much computer science into you as I can. One of those, of course, is the midterm. That's 2 weeks from 2 days ago, or Wednesday, 2 weeks from this week. So that's going to be an in-class midterm, just like the previous couple. We're going to finish arrays probably middle of next week. we're going to spend some more time talking about other class issues. Other than homework 9, any other questions, comments, or concerns? All right. So this is homework 9, and look, I can make it bigger. Whew. In particular for this one, I'm not going to spend too much time talking about it, but you're going to have to implement the party class and the vehicle class. The vehicle class is going to be somewhat similar to the other classes you developed. It has a couple properties, it has a couple access or mutator methods. There is only one method that's going to be fairly difficult. That's the move method. All the other methods, you have the normal accessor and mutators, and then you have things like add to money, which instead of, as opposed to set money, it just takes it and adds to the money instead of just directly setting it. The other class is the party class, and the party class, blah, 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 blah. The party class has a 1D array of persons. And the 1D array of persons is what's going to, it's basically the homework on 1D arrays. You're going to be adding people, essentially this 1D array is going to hold all the members of your party. And you're going to be able to add people to the party, and essentially you're going to pass a person object into a method. It's going to shove it into the array in some particular fashion. And then it's going to go about manipulating that array. So that's really going to be the 1D array homework, whereas the 1D array lab, of course, was yesterday. And at least the lab I got fairly good, I actually got pretty good feedback on it. A couple people said it was too long, but a lot of people said they really liked it. So that's essentially the basis of this homework. Yeah, there's a vehicle class, which is going to reinforce a lot of the other creating class techniques, but it's really the 1D array that we're looking at here. In terms of remaining classes that need to be done for this, so we talked about this diagram last time. I'm not going to spend too much time talking about it. Blah, 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 blah. All right. So there we go. There's a total of 5 classes that you have not yet, as of this point, implemented. Map, party, vehicle, control, and map printer. Map printer is going to be next week's lab. That's the lab dealing with 2D arrays. Map is going to be homework 10. That's the homework dealing with 2D arrays. Party and vehicle are going to deal with party and vehicle are in the current homework. And then I think we'll probably just give you the control class. That's another thing. I was afraid that if we, and this isn't definite, but I was afraid that if we assigned it, it would end up being another homework 8 issue. So we probably will just give you the control class so that if you want to sort of see how the game works, you can look at it in great detail. But essentially, that will complete the game, and then we'll have a ideally fully functioning game. So that's in terms of what's left. Okay. Right, we saw that. So my TAs felt that just having pictures of me available getting pie in my face was not sufficient, so they put a YouTube link up, which is the same user who has the sonograms on the YouTube link. That's the TA, Rebecca. That's a student in this class who I will not reveal the identity of. So yes, that was me getting pie in my face. So I was actually, they did it with a number of faculty, about a half dozen CS faculty went through it. And so Professor Humphreys and Professor Hazelwood, they're 2 faculty members, and Professor Hazelwood was sitting there actually right as I was coming to class on Wednesday, and she was in the, her head was through that hole. Professor Humphreys was having a field day with this. He spent so much money trying to get pie on the face of all his colleagues. And what everybody did was they took the pie and they tried throwing it. And of course, pies don't throw very well. They're not very aerodynamic. He instead took it and just scooped it and kept nailing her in the face every time. Her face was completely... So she went home. She said she washed her hair 4 times. It still smelled like rotten eggs. And she had to shower, and wash it another 4 times the next day. I was really glad that he didn't know when I was going up there, because he would have been out there in force. And all right. So I want to continue with arrays. I want to spend some time finishing up our talk on searching. We had done some searching stuff last time, and there was some confusion on sequential search. So I have these fancy schmancy PowerPoint animations that I'm hoping will explain a bit better. And this is searching, and then we're going to talk a bit about sorting and then come back to the whole searching thing all over again. So this is the sequential search method that we saw, right? And I'm going to go through and trace it. And let's say that we call it with that. We have a explicitly initialized array that has a total of 6 elements in it. We're going to search for 11, which is, as we see, at position 3. It's the 4th element in position 3. So the method is called, and we pass in that array as data and that number as the key. And that's what it looks like. Int I equals 0. That's going to declare an integer variable I and give it value 0. Now, this I is actually going to be an index into the array, because we're going to say data sub I. So I'm going to draw it like a pointer. It's not really a reference, but I'm just drawing it that way because the whole point of this is that it's an index in the array. So this arrow is again, this is an int. It's not a reference, but it's just showing you which element in the array it's looking at. This loop is going to continue while I is less than data.length. There are 6 elements in the array. Data.length is going to be 6. I think we can all agree that 0 is less than 6. It checks to see if data sub I is equal to key. In this particular case, data sub I or data sub 0 is 6. That's not equal to 11. That condition is false. It's going to loop around to the next iteration of loop. I gets incremented. And again, this is the pointer, if you will, to the spot in the array. It checks the condition again. 1 is less than 6, so it's going to keep going. It checks to see if 9 is equal to 11. It's not. It doesn't bother returning that value. I is incremented to 2. I is less than 2 is less than 6, so it's going to go through again. 11 is not equal to 82. That gets incremented to 3. 3 is less than 6. And now it checks to see if 11 is equal to 11. It is, right? Because data sub I is data sub 3. That's spot 11 is equal to key. We are now going to return I. What this method returns is the position in the list, or the first position in the list that that element was found at. It does not return the element because that was actually passed into the method. It returns the position. I is 3. That's what's returned by this method. So back down to this line, it's going to create an I1 variable and set that, equal to 3. Yes? If there's more than 111, it just returns the position of the first. You could write something that maybe looks for the last one or finds all of them. This just returns the first occurrence of, we return the first occurrence of 11 if 11 was in the list multiple times.
How does data become the same score?
Score is passed in, and remember what happens is that score is really a parameter, a reference to some array. So what actually gets passed in is that reference. So in reality, both data and score are references to the same array. It just happens to be this particular array. How many people felt they sort of understood that? Okay, I'm seeing a good number of hands. So that, of course, is what happens if it does find something in the list. This fancy schmancy animation is what happens if it does not find something in the list. So now we're searching for 30. That's pretty much the only difference from the previous slide. And as you can tell, 30 is not in that list there anywhere. So it goes through the same thing, and essentially int I is equal to 0. That's really a pointer. And as we start going through it, I keeps going through the list, right? It keeps doing, well, I is less than data.length, checks to see if that element in the list is equal to what we're looking for. No. Imagine that I had actually done this correctly, and there we go. Okay. Now let's try this again. We're searching for 30 because that's what was passed in as a particular key that we're looking for. And again, int I is equal to 0 creates that. It's going to keep doing this while I is less than 6, because 6 is the size of the array. Checks to see if 30 is equal to that particular element. If it's not, it loops around. I gets incremented. Checks to see if 9 is equal to 30. It's not. I gets incremented. And it keeps looping around, moving through the array in that fashion. So at some point, I is going to become 5. So it checks to see if 5 is less than 6. It is. So it's going to keep going through the array. It's going to check if data sub I, or 85, is equal to key. It's not. That's false. So we're going to increment I again. I becomes 6. This check will keep doing it while I is less than the length of the array. Well, at this point, 6 is not less than the length of the array, because 6 is not less than 6. So this entire loop will terminate because we have not found the element. So essentially what this does is this sequentially goes through the array one by one, keeps going through until either we find it, as in the previous example, or it run right off the end of the array. In this case, I is not less than the length of the array, meaning we've checked everything in the array. We're going to return -1. Remember that -1 is a placeholder. It's just a means to allow you to notify the sender, or I'm sorry, the caller, that the element was not found in the array. So then I1, which is down there, then becomes -1. How are we doing with that? How many people feel they sort of understand that? Okay, I'm seeing a good number of hands. All right.
So basically, it's going to keep going around and around.
The loop goes around and round. It goes throughout the entire array until it either finds it or hits the end.
Is it ever possible to return a different type than the method type? Like if you wanted to return a string, we didn't find it. Is there a way to do that?
The question is, what happens if you're searching for strings and you don't find it? Typically, in that situation, you return null.
No, I'm saying like if you don't find what you're looking for, can you return a string instead?
Oh, the question is, can you return any? There are ways to play with the return type of a method. We'll actually see that a bit on the last day. Okay, that's getting much better. If you remember, the peak was most definitely, it was a nice bell curve last time. We're moving over towards the very well understood, so I'm glad. So the sequential search will, when properly implemented, will definitely find an element in the list. The problem is that it might take a long time. If you have a list, if you're searching through a phone book, and you have 1 million people in the phone book, and you do a sequential search, you're going to have to go through 1 million entries before you find Mr. Z. So there are ways to make searches much faster, which is what we're going to spend some time talking about. But before we do that, we need to talk about sorting. In particular, given some list, some array vector, we often want to put that vector in order so that the lowest element, however you define lowest, it could be numerically lowest, it could be earliest in the alphabet, is first in the list, and the highest element, whether that be numerically highest or towards the end of the alphabet, is last in the list. And generally, this is how humans look at, when we look at lists, we humans usually have them sorted. My class roster has people with the last name of A well before people with the last name of Z. Or if it's sorted by social security number, or UVA ID number, which is really the same thing, it sorts that numerically. They don't tell us that anymore, which is a good thing. But so the standard order is called non-decreasing, which is kind of like increasing, but not quite. I think we could all agree that that is increasing order. Every element increases from the one to its left. But what if we had two 5s? A couple 6s, a couple 7s, and an 8. This is how we would probably sort it. We group the 5s together, the 6s together, and the 7s together. And that is still, we could argue, in sorted order. But you'll notice that this is no longer increasing order, because this element does not increase from that element. And those elements don't increase from one another. Neither do these. So technically, this is not considered increasing order because there are some elements that stay the same. It is called non-decreasing because from one to the left, it either stays the same or goes up. It never goes down. So what we need to do first is we need to be able to compare elements. We can compare numbers pretty easily. Strings, it turns out, is a bit harder to compare. Sure, A is before Z, but is capital A before capital or lowercase z? And at that point, it starts becoming a bit more difficult. Or what if you have what's he called now? The artist, or the artist formerly known as Prince, when he had his name as a symbol? How would you actually compare that to stick him in a phone book? Somehow I think he's unlisted. And what we need to do is we need to take some array, and we're going to move things around so that it is in sorted order. Here we have our array, B. And there are 10 elements, which correspond to the top row on a keyboard, QWERTY, UIOP. What this algorithm is going to do is going to go through it and sort this particular array. And essentially what it does is it's going to go through a number of what's called iterations. This array is 10 elements long. It's going to go through 10 iterations. On the 5th iteration, it's going to ensure that the first 5 elements are in sorted order. On the 6th iteration, the first 6 elements will be in sorted order. On the 8th iteration, the first 8 elements will be in sorted order. And what it does, so the first time it's going to go through and find the lowest element or the minimum element in the list. In this case, I think that's E, right? Yes, that's E. So it's going to find E and move it to the first spot. Then it finds the letter immediately after E and moves it to the second spot. And the next couple slides actually illustrate this. So iteration 0, it's going to go find the smallest element in the array. And that smallest element happens to be E. So what we do is we're going to take E and we're going to take the element in the first spot and we're going to switch them. Now, at this point, the leftmost part of the array, or the yellow part of the array, is properly sorted. It has the lowest element in the array, or lowest elements, in this case just one, and they're in proper order. Iteration 1, it's going to find either the second smallest element in the array, which is I, and it's going to take I and move it into that spot. And those two get switched. Now the leftmost part of the array, again the yellow part of the array, is properly, just these two are properly sorted. It contains the lowest and the second lowest elements, and they're sorted in proper order. Now we're going to find the third smallest element in the entire array, or the way Java looks at it, the smallest element in the unsorted part of the array. So it's just going to look at the blue part. It's going to find the smallest element in the blue part, O, and it's going to swap it with the element in that position. So O and Q get swapped, and again, the left three most spots are now properly sorted. It again finds the smallest element in the unsorted part of the array, or the blue part, and it's going to swap that with R. It finds Q, swaps it with T, et cetera, et cetera. And so that's what I mean by when I say after the 5th iteration, it says iteration 4, again, is counting from 0. So after iteration 4, all spots, the left 5 most spots, are properly sorted and contain the lowest elements. Again, however you consider lowest elements. Earliest in the alphabet, lowest numerically, sorted alphabetically. And this is called selection sorting. Because as you go through it, you're going to go and select the next smallest element and move it into its right position. I'm again going to select the next smallest element, or the smallest element in the blue part of the array, and move it to its proper position. This is extremely slow. It would take forever to sort very large lists. There are much better ways to sort, which you're going to see if you take 201 or 216. But this will get a list sorted. It's just going to take a bit of time. So if we were to actually look at the selection sort algorithm, this is going to go through the entire length of the array. It's going to move through, look at each, it's going to move through, let's try this again. I is going to go through every particular element in the array. What it's going to do is on the ith iteration, it's going to find the smallest element in the blue part of the array and swap that and move that all the way to the left. So on, going back a couple slides, here on iteration 2, it's going to find the smallest part in the second part, the smallest element in the blue part of the array, and swap it here. A couple things to note. We are on the wrong pen color. Pink?
Yeah.
That pink?
Yeah.
Okay.
The next one.
That pink?
Yeah.
Okay. We're on iteration 2. And what we're going to do on iteration 2 is find the smallest element from spot 2 to the end of the array and swap that element with the element in position 2. On iteration 3, we're going to find the smallest element from 3 up and swap, which is P, and that's we're going to swap that with the element in position 3, et cetera, et cetera. So what this does is this finds the smallest element from whatever iteration we're on until the end of the array. This keeps track of what the smallest element is. And then when we do find it, it's going to swap those two elements. It's going to take the element, the smallest element it's found, put it in the right position, and take the thing that was in that position and put it into where the original element came from. So that's essentially what selection sort does. Blah, blah, blah. So I didn't go through an actual trace of the algorithm. I'm thinking more high level. How are you feeling with selection sorting? Okay. That's good. I mean, that's about where I wanted to be at this point. I'm introducing this to you because it's something that's done very often with arrays and such. I think what I'll do is I'll try to work up some more slides for Monday. So every year they come out with new demotivators. And they did this for many, many years. And the problem is some of the demotivators they came out with, because they were coming up with 12 every year. And you could tell that after a while, they kind of ran out of really good ones. And they come out with 12 new ones. Some are really good. Some are just kind of dippy. So this year, they're just coming out with ones that they think are good rather than forcing 12 out. So these are new ones that came out in 2008. Customer care. If we really cared for the customer, we'd send them somewhere better. Consistency. It's only a virtue if you're not a screw-up. Not so good? So let's talk about another type of search. So we talked about sequential search, which starts at the beginning of the array, works its way until the very end, and at the very end, either it's found it or, when it finds it, it says, great, I found it, hallelujah. If we hit the very end and we haven't found it, it returns -1. This ends up being very slow. Again, the phone book analogy, you have a million things. You don't want to have to search through it one at a time. So people have come up with a much better means of searching, and this is called the binary search. The idea is, same thing, given some list, we want to find what element, or where the element is in the list, or -1 if it's not found. As far as the user is concerned, it will operate the exact same way. You give it a list, you give it a key, it gives you the position that that key is in the list, or -1. A binary search requires the list to be sorted. Sequential search did not. It couldn't care if the list was sorted or not. Binary search requires it to be sorted, and we'll see why in a minute. And essentially, if you have a million elements in the list, a sequential search is going to take, worst case, a million steps. If your last name is ZZZZZ, and it's searching for you in the list, it's going to have to go through all million people in the list before it finds you. Binary search will take 20 steps. So, not surprisingly, it's a heck of a lot faster. So this is the algorithm to actually use it. The BS stands for binary search. Here we create the numbers. We print them out with the print list method. We do a selection sort on it, so that's going to ensure that it's in sorted order. We print that out. And then we do a series of searches for it. If I was to actually run this code, that I want to end 2, and you'll see that it more or less, it works as desired. Well, if you could see it, you'd know that it works as desired. There we go. This is our list, 1, 2, 3, 4, 6, 8, 9, 10. Some of these are found, some of these aren't. And it will return the index where they're found. The number 4 is at index 0, 1, 2, 3, so that's why it's giving 3. 5 is not found, 11 is not found, etc., etc. So I think we can all agree that it works the same way, and now I want to show you why it, how it works. So this is the algorithm. All right, got it? So essentially what it's going to do is it's going to look at the middle element of a list. Let's say you're searching the alphabet. You're searching for Smith. It looks at the middle element, and it's, I don't know, N. Well, you know that the first, if that's the middle element, the first half of the list has A to N, and is definitely not, well, this is from your point of view, it's this way. If the middle element is N, A to N is not going to have Smith in it. It's going to be in the second half of the list from N to Z. So what I can do is I can completely get rid of half of my list. I know that in my sorted list, the A to N half of the list is not going to contain somebody with the last name of Smith. It's going to be in the second half of the list. So now I just look at that half. I'm going to look at the middle element. What's middle between N and Z? Q? No, that's probably not element. I don't know. T. Let's say N to T is in the first part of the list, and U to Z is in the second part of the list. Again, U to Z is not going to contain Smith, so again, I've cut my search space in half. When I say search space, I mean the amount of elements I'm actually searching for. So let's actually do a trace. I'm looking for 14. That is my list. Imagine that the name of the list actually matched the index. Int I is 0. an int. Now, I is going to be a index into the array. Again, I'm putting arrows here because it'll help us see what's actually going on. Int j equals data.length minus 1. So this I in j represents a range. And the element I'm looking for, 14, if it exists in the array, is somewhere between spot 0 and spot 9. Right? We've just started, so we know it might be in the list somewhere. We have no idea where. We're going to say, well, I is less than j. While that's true and 0 is less than 9, I'm going to find the middle spot. I plus j over 2. Well, 0 plus 9 over 2 is going to be 4.5. This is integer division, so m is 4, and that's the middle of the array. I'm going to compare key, which is what I'm searching for, 14, to the element in the middle of the array, 10. I know that everything to the left of that is going to be 10 or less, and everything to the right of that is going to be 10 or greater. So because 14 is greater than 10, I know it's going to be in the right half of the list, if it exists. In this case, it does. The next slide, we're going to see one, or two slides, we're going to see where it doesn't exist. So 14 is greater than 10, so I can completely get rid of this part of the list, and I'm going to say I equals m plus 1. So now I is equal to 5. Now what this is saying is that if 14 exists in my list, it's somewhere between position 5 and position 9. So again, I'm going to find the middle element. 5 plus 9 is 14, divided by 2 is 7. M is the middle of the array. It checks to see if key is greater than 16. Well, in this case, it's not. Right? 14 is not greater than 16. So I know if this element exists, or I'm sorry, this element exists in the array, it can't be to the right of my middle element. So I'm going to say j equals m. Again, I've narrowed my search space. I've cut it in half, as much as you can cut a non-power of 2 in half. Now, if this element exists, it's going to be somewhere between 5 and 7. Go through it again. M is I plus j over 2. That's 6. If key is greater than 14, well, it's not. So I'm going to do that one and say j equals m. Goes through again, figures out the middle of those two elements. Well, 5 plus 6 is 11, divided by 2 is going, integer division by 2 is going to be 5. So m is now pointing to the same spot as I. If key is greater than 12, it is. I is going to be the next spot over. Well, I is less than j. In this case, 6 is not less than 6, so the algorithm ends, or that while loop ends. At this point, if the element is in the list, then I and j, or specifically I, will point to where it is in the list. So we check to see if the key is equal to the element at that position. It is, so we're going to return 6. We've found our element. What we did is every time we cut the search space in half. How many people feel they sort of understand that? Okay. And return 6. So the question, of course, is what happens if the element is not in the list? Same thing. Now we're looking for 15, which, given our particular list, is obviously not there. It goes 14 and 16. Again, the list must be sorted. So we're going to go through the same algorithm. I starts at 0. J starts at 9. The middle element is 10. 15 is greater than 10, so this algorithm is going to cut out the left half of the list. Now it's just looking at this part of the list from index 5 to 9. Looks at the middle element, 16. 15 is not greater than 16, so it's going to shrink the list that way. Again, I've cut it in half again. M is going to be the middle element. Key is greater than data sub m. So yes, 15 is greater than 14. So I equals the next spot over. At this point, I is not less than j. 7 is not less than 7. If this element exists in the list, it will be at data sub I. So this while loop finished, if it exists in the list, it will be at that particular spot. But it turns out that the element at that spot is 16, not 15. What it's saying is this is where 15 would be in the list if it were there. Well, 15 is not equal to 16, so I'm going to return -1. That element was not found.
It seems like this only checks the right side, like if it's greater than like the midpoint. Because if you were to put in like 5 or something, it seems like it doesn't check the left side of that.
Oh, so the question was is that I'm just looking at the right half of the list? The question was I'm just sort of looking at the right half of the list. That was I had to pick a particular element to search for. I picked just something on this side of the list that would get it to bounce back and forth a bit. I didn't want to do a completely different animation to do the left side of the list because it takes me like an hour to do these animations. But yes, if you would search for 5, then it would certainly be focusing on those elements.
So, I mean, the key will never be greater than data.
No, it will still do it. It's just after the first iteration. I'm pink, right? After the first iteration, it would look like that, right? And then if you're looking for 5, the next iteration would look like that, and then like that, and it would sort of narrow it down on the left side of the list. Okay, how are we doing with the binary search? Okay, doing well. So here's a slightly different take. Here I have a phone book. This is my sorted list. Ross, pick a name. Last name. Smith? Smith. I look in the middle of my binary list and I get Powers. We'll search for Powers, his last name. I go to the middle of my binary list, computers. Is it before or after computers? It's after, right? So I can get rid of the first half of my list and I've just cut my search space in half. I then take the remaining part of my list and search in the middle. I get mulches. Is it before or after mulches? After. I take my search space, cut it in half, and again, I now have half of the previous spot. I take a look in the middle of my list and I get roofing. Is it before or after roofing? And I continue to tear apart my phone book, search my list, cutting it in half each time until I narrow down to the particular spot in the array where Powers is found. How's that for a binary search demo? You know, the scary thing is that I actually got that demo from this one person who was one of the worst instructors I have ever seen, but he had that one really good demo. Go figure. So how long does a binary search take? Yes. I save phone books for this, by the way. And my folks that get these really big phone books, so they live in New York, I tell them not to throw them away. So every time they come down, they bring me the stack of phone books, but they always bring me the wrong one, so I just recycle them. Yes?
The binary search takes less time than the sequential search, assuming that you already have the list sorted.
Yes. If the list is not sorted, then the binary search doesn't work.
Well, you have to sort it.
Yes, you would have to sort it first and then search, and that would take a lot longer. But for something like looking through if email's coming into UVA and it goes to, I don't know, ZZZ9Z is the address it's going for, ITC has all the email addresses sorted already, so it can do a very quick search. Let's say we have an array of 64 elements. The first iteration is going to cut that list down to 32. It's going to be in the first half or the second half. It's going to get rid of half of them. Second iteration cuts it down to 16, then to 8, 4, 2, 1. It takes a total of 6 iterations to find an element in a list of size 64. What if we had 10,024, just over 1,000 elements? The first iteration would cut that down to 512. The second iteration down to 256, 128, 64, 32, 16, 8, 4, 2, 1. It's going to take a total of 10 iterations. Sequential search would have to go through one at a time. But a binary search, so sequential search would take about 1,000 times. A binary search can do it in a total of 10 iterations. In particular, the number of iterations it takes is the log base 2, meaning the power of 2 that equals that particular number. 2 to the 10th is 1024, 2 to the 6th is 64, et cetera, et cetera. Right, where n is the size of the array. So let's say the array has n elements, whatever n is. Sequential search is going to take n iterations. This is worst case, right? If you're looking for someone with the last name of Z, it's going to have to go through the entire list. Binary search is going to take the log base 2 iterations. If you had 1 million elements in your list, such as searching through a phone book within, okay, Charlottesville doesn't have 1 million people, but I don't know, pick a city that has about 1 million people. Richmond is probably roughly in that population range. A sequential search takes 1 million iterations. Binary search takes 20. Let's say you had a list of 1 trillion elements. You might say, well, where the heck are you going to have a list of 1 trillion elements? Can anyone think of one? Begins with a G. Google. If you look at it, they have somewhere in the range of 1 trillion web pages that they need to search. If you did a sequential search through all those web pages, actually they do a lot of really fancy search stuff that I'm not going to get into here. But if you had to search through 1 trillion web pages to find out, I don't know, the YouTube of your professor getting a pie thrown in his face, it would take a really long time. A binary search takes 40 steps as opposed to 1 trillion steps. That's something that a computer can do in no time. You wouldn't even notice the delay. Right. Sequential search takes 1 trillion iterations. How are we doing with binary search now? Okay, it definitely moved a bit more over to left, so that's a very good thing. So I wanted to, before you go, I wanted to leave you with one of the better and more creative commercials that I've seen. So this commercial was not done with any computer graphics. That's pretty good, huh? You like that? Oh, there we go. Right. Tell you what, I'll show that to you next time. Have a good weekend. I'll see you on Monday.